So thanks, for inviting me to this seminar. I see that you folks have been running this for a while. So it's a pleasure to give a talk here. All right, so this is work with a lot of collaborators. I'll show you who they are in a minute. But I'm from University of Delaware. If you don't know where Delaware is, it's about 90 minutes train ride from New York, Manhattan, if that helps put things into perspective. So towards the East Coast in the US. So this work is basically several years of work with many scientists in the making, where we have been trying to, try different pieces of using HPC, AI, machine learning throughout the process, and lots of tangible outcomes have come out of this work in the past, several years, honestly. So to quickly give you a background of my group, so this is my group in Delaware, research group, PhD students, masters, and a lot of undergrad students. We do both foundational work as well as interdisciplinary science work, where we build, compiler implementations and open source compiler toolchains, LLVM, for example. We explore directive-based programming models, OpenMP and OpenACC, for real-world applications, migrate them to large supercomputers. As you know, that is easier said than done, right? So it exposes a lot of challenges, both in the hardware and the software framework. So we, work our way through those. In the last 4 or 5 years, we have also been engaging with local hospitals with their data sets and building predictive models for cancer research. So there is an ML and AI component over there. And very recently, we started to use large language models for exploring how we could generate tests to validate compiler implementations for OpenMP as well as OpenACC, which are, you may know this, directive-based programming models for C++ Fortran. So that's a group, and many, many thanks to all the funders who have, enabled research in the last several years. So this project, while it's, primarily focusing on Pick-on GPU, particle and cell on GPU, the long and the short of it is there is a grander challenge, right? As you know, there is a lot of applications which have a ton of data set, volumes and volumes of data set, and sometimes it isn't feasible to envision all data set all at once in one big dashboard and try and extract sensible information out of this data set, right? So you could think of data reduction, but data reduction also need to be done cleverly so you're not losing meaningful info. So we often struggle to put a pin on the scientific questions when we're dealing with, data set beyond what our machines can handle, right? So that being the question, we are wondering how to do this, how to build a framework, how to build a methodology where we can look into large data set. Sometimes it is simulated data set, sometimes it is directly from the source, from the experimental source. How do we analyze, all these incoming data without losing information, yet answering important questions? So I'm throwing some examples here. The left side image, as you can tell, looks funny. So that is ChatGPT, DALL-E created maybe a year ago or so. I don't think all the pieces in the globe is making total sense, but since I have probably burnt some trees generating it, I decided to use it anyway. My prompts were system models, land, sea, ocean, all those models that you usually find in big codes like ICON, for example, ACMWF, for example. MPAS A and O are from National Center for Atmospheric Research here in Colorado. So basically, again, going back to the philosophy of lots of data set, right? The right-hand side is a pretty famous picture from CERN. Petabytes, terabytes of data per day sometimes. So there is a lot of questions to be answered. Diving into the real topic here, which is plasma physics. I learned about plasma physics from my collaborators, HCTR, the Helmholtz Zentrum, Dresden Rosendorf group, about 2019 when we started to work together on their Pick-on GPU, plasma and cell on GPU code. Plasma physics, I'm not a physicist, I'll try my best here, but the bottom line is diverse data properties. There is microscopic particle interactions to macroscopic magnetic field. Again, we are dealing with lots of millions and billions of particles, right? One of the phenomena we have wanted to explore is the plasma instability phenomena. And as I get deeper into some of the results and stuff, we would focus on that particular idea in particular. Something I wanted to point out is perks of a computer scientist working with a domain scientist. You get those pretty pictures, as you see on the right. Kudos to the team for every now and then creating images using, the in situ visualization ISAC framework. That particular one is Felix Meyer, and he had tried to create this on HDR Chimera cluster for NVIDIA V100 GPUs. So every now and then we would stop and pause and try and generate some of these beautiful images to visualize some of the scientific phenomena. Coming back to the plasma instability implications, as you know, the implications are multifold in different fields. Not long ago, I think September 2024, which was last year, Delaware, which has never witnessed the Northern Lights, Aurora Borealis, we witnessed it here. It was impossible. It is unimaginable, right, that we are able to see these beautiful lit sky all of a sudden. As you know, that's because of the geomagnetic storm and, the background phenomena is plasma instability there. There is magnetic reconnection implications, solar flare, and sometimes, sudden violent reaction and fusion research is also because of the instability in blood plasma field. So implications is many, and that was another reason we decided to study a little deeper into this particular idea. Long story short, what we wanted to learn is how could we map back some of the learnings from the machine learning network to the original input data, right? So it's an inverse problem. How do we reconstruct, if possible, completely phase-space observations to get a detailed view of the growth and dynamics of instabilities? There is another beautiful picture there on the right-hand side, as you can see. It's Rene's from, again, Chimera cluster. So this learning phase, this complete reconstruction can otherwise, lead to a lot of complex simulations, a lot of complex, experiments that can take quite an amount of time, right? So how do we detect, how do we extract meaningful info and be able to put this reconstruction together? So that's why a really large group, as you can tell, lots of physicists, visualization experts, research software engineers, computer scientists, and in situ analysis experts, and so on. So majority of the team is an HCDR. At my end, PhD students have been part of the group. Masters and undergrad students have learned volumes by working with several of the collaborators. Very grateful to the Center of Excellence, COE, which was the HPE, Cray, AMD folks as part of the Frontier supercomputer at the Oak Ridge National Lab, which was where we started to work on this project. As you know, Pick on GPU did not start in Frontier, it started way back. It's also a Gordon Bell runner-up for 2013. And the code was running on Titan, and then it ran on Summit, and now it runs on Frontier and many other systems across the globe. So many thanks to ULISH Supercomputing Center as well. At some point, we'd used their system, and thanks to the funders and the group that we have been working together for the last actually 5 to 6 years, which is really, really, really wonderful. So that basically shows the laser plasma accelerator tearing through the gas chamber, displacing electrons, creating a wake, thus accelerating the laser particle accelerator, creating this high energy accelerator, which is what our end goal is. And this is also a nice visualization by Vincent using ISAC, as you can see in the footer. So while we are brainstorming different case studies of Pick on GPU that would benefit from different computing resources, this particular one is Laser Wakefield LWFA accelerator that we started to first look into a little bit more deeper, right? So Pick on GPU applicability is in material science, radiation therapy of cancer, and I believe the HCDR colleagues work with local hospitals as well, and the high energy density physics and so on. So the challenge was, or let's say where we started this particular application was back in 2019 when baby frontiers were being built in Oak Ridge Lab, where the goal was, hey, let's pick some well-known applications that could stress test the upcoming hardware software stack of Frontier, right? So this was a challenge program called CAR, which is a Center for Accelerated Application Readiness from Oak Ridge Lab, with the goal to stress test Frontier as they were building Frontier from 2019 through 23-24, right? So we were tasked with, could you get 4x better performance than what the code has given you on Summit, which was an IBM and an NVIDIA V100 box. And as you know, Frontier is all an AMD shop, right? So this is where we started. And the left-hand side is yet another image of LWFA with 48 NVIDIA V100s by Felix Meyer and Richard who perhaps is on the call. We also had a metric for our code, which is the form run that we needed to meet the 4x performance. So that's a crux where it shows what are all the systems Beacon GPU really targets, starting from Titan, Summit. Perlmutter is in Lawrence Berkeley National Lab over here with the NVIDIA A100s. Joules Booster, another A100 system. We had a test H100, Hopper 100 box from NVIDIA, so we threw it on those. Ulish is Hopper 200 GPUs. Frontiers, of course, the AMD MI250X. As you can tell, I've slightly color-coded the bullets. There was also a test bed from Oak Ridge Lab with Ampere computing CPUs based on ARM. So we throw the code wherever we can because it opens up a lot of software and hardware questions, which makes the research angle very interesting, right? So long story short, there is a full user guide on the entire system, but to just put things into perspective, we are looking into X number of cores, X number of GPUs, the beast, as you can tell, over 37,000 GPUs, and MI250X typically has 2 GCDs. So this was a funny thing that we went through in iterations because we would say GCD, somebody else would mean a GPU. These were all lingos in the very beginning of a Frontier system, right? One GPU, MI250X, has 2 GCDs. So technically in a single node of 4 250X, you're dealing with 8 GCDs. But if you were to use Slurm, Frontier, it will allocate you 1 GPU, which technically is 1 GCD. So quirky things like this, which threw our performances off every now and then, and we would come back to the drawing board and analyze what went wrong. Anyhow, so system interconnect, the storage capacity, how many nodes, approximately 9,400 nodes, etc. Right? As you can imagine, with any large code, you have all the challenges that's listed here. So there's a portability issue. You don't want to compromise on performance because your code is portable. You want to make sure your code is scalable because we're talking about over 9,000 nodes, right, with 4 GPUs per node. And any scientific application is only more appealing when you can practically visualize what's happening within the program. And until I got into this group, I had no clue how these applications are usually visualized scientifically, right? But working with the group, it is a Herculean task to actually get these visualizations to the T, right? What looks great to a computer scientist may not necessarily look as correct as it should be for a physicist. So those were some, lessons that we were learning along the go. And exascale workflows, because you're talking about in situ analysis, you're talking about data reduction, and even visualization at scale, right? So you can imagine in an exascale computer like Frontier, anything that can go wrong does go wrong, and it did go wrong. And then you iteratively try and work your way through and making the code better. So how was all this even possible for Beacon GPU is via Alpaca, which is the software stack which the code uses under the hood. Alpaca is being developed or has been developed over the last several years. You can see some citations in the bottom. And it has multiple target platforms, which is how the code was even remotely feasible to move from a full NVIDIA GPU box to an AMD GPU system, right? So it has multiple backends. It's a software stack that is developed as we go. So it is. We had to do a lot of Alpaca development as well under the hoods as and when the Frontier was being built. So let's start with a base run, which was 2019 November. This was we needed a base run, right? So to appreciate the performance numbers that we would get later. So this was a form baseline run, teraupdates per second is our peak form, a figure of merit as you see, and there's an average. There is a sustained as well as peak power on Summit, and these are all the parameter details, right? So this is where we started. Fast forward, major improvements to Beacon GPUs since Summit 2019. Of course, algorithmic improvements, physics improvement, performance optimization. So both computationally as well as scientifically, lots of improvements along the go. So you can see some number of commits in the bottom of the slide. And we used to, I think Rene's used to call it Red Queen's race, because if you're staying in the same place, you're falling behind, right? So we had to continuously keep updating several pieces of the software. And this was also back when AMD did not have their RockProf or OmniPerf performance analysis tools. They were being built as we spoke. So we had to often whip up Python scripts, whip up our own roofline models, our own performance analysis tools, sometimes defaulting to NVIDIA Inside Compute and System to see how the code performed on an NVIDIA GPU and relate that to, theoretically how it could have performed on an AMD GPU, because we didn't have the tools to poke deeper into the GPU. So that was one of the journals we wrote, published in ACM TOPC about, metrics and designs back then, instruction roofline, not necessarily floating point, for AMD GPUs. So right from the start, right, you're working on a system whose software is being ROCm with, or HIP is evolving as you speak. Hardware is evolving as you speak. So the code has run on MI50, MI100, MI200, MI220, MI250X towards the end. And every step of the way, you would notice that there are backward compatibility issues, or there is incorrect information ROCm would give at some point, which we would point out. The team, the Alpaca team, put so much effort that every time we were opening a GitHub issue with ROCm, we would also, the very most, give a potential solution, right? Because you could fix the problem right away and move on, but it is not sustainable, right? If you just create workarounds, it has to be fixed to the bottom of it, else somebody else is going to suffer. So we wanted to make sure that all the bugs are, fixed to the T, so that it's a sustained solution. And all this takes months, right? Months of effort. So this used to be my constant, call it a quote, call it a, hey, people, you got to listen to this, feel to the vendors, that you can build a beautiful hardware, but if your software and tools don't speak to the hardware is not good enough, right? At the same time, we had so many tickets, so many issues, created with HPE, with AMD, with Frontier, with OLCF. It was very critical to make sure that everybody were on the same page, that we're looking at these tickets. So communication between developers and us users were key, right? I remember texting, calling people on the phone to give them a GitHub issue number, for example, but it had to be done on time, along with trying to find solutions, else it was going to fall through the cracks. Okay, so some drum roll moments. So this was, the baseline, as you can see, is the first bar plot of 14.7 terabits per second, 2019. Then you see the shades of green, 18.6, 1.26x, which was projected on Summit. In 2022, why projected? Because the algorithms, the code evolved, right? So backward compatibility is an issue if you're dealing with an older version of compilers and stuff on Summit. So most of these are projected code because we are moving forward, and it didn't make sense to use, previously dated tools and compilers to make our forward-looking code work. So some of these numbers are projected. Around 704 nodes is where we already saw the 4.08x speedup, where we had met the car form figure of merit target. Back then, I think those were the number of nodes available. Few months later, we also got access to about 9,260 nodes, where we saw the 4.4x speedup. It's all single precision code, 65.7 terabits per second. So that's when we had met the car form target. It was a drum roll moment. We had made it work after 3-4 years of, dancing around the code and the hardware and the software and dealing with all the vendors, etc. Bugs and stuff, right? For the fun of it, we also tried to put through a double precision code, and we saw even better a speed up for a double precision code. Okay, so this is a plot with Frontier. The two columns that you see this one is on Frontier, right? So this is just how much more signs or how much more particles you could process on Frontier compared to Summit. As you can tell, it ran sustained peak power of 23 megawatt. I don't know if we should be happy or sad about a core running for about 6 minutes at 23 megawatt, which could practically lit up an entire city. So that goes back to what kind of algorithmic improvements we could do for better power usage. But having said that, from the Frontier angle, we built a system of that powerful system, right? Pun intended. And you see a code that's running at that, at peak power, it feels, somewhat, okay, so we actually built a system that benefits a code that's running at that point, right? So those were some plots and numbers and form runs. Now, this is a weak scaling run, 6 nodes to 48 to 96, 98% GPU utilization, Frontier and Summit, as any real world application, which is mostly memory bound code, and This is a plot that basically shows that it also weak scaled on Frontier pretty well. So while as a computer scientist with my hat on, I was pretty excited that the code met the form run and we got 4x performance, etc. I didn't quite see the spark in the physicists, right? And we wondered, okay, so we did this computationally, it solved, or we met the goal. But scientifically, what question did we answer, right? While we may have answered a few questions, but the point was Frontier could only perform a few long-running simulations, but the parameter space, as you can imagine with any of these real-world applications, is huge, right? And it also requires a sophisticated workflow to advance the science and to answer some more compelling questions. So we needed to close the gap between the simulation scenarios as well as the experimental setup in the lab, because experimental source is going to throw a lot more data at you, right? So it is not enough if you're only running a few long-running simulations and be happy with the current output. So that made us go back to the drawing board, and then came the plasma instability angle to the story that we did an LWFA, great, but let's talk about what other cool physics problems we could solve. And all that leads to terabytes of data, right? Trillions of particles, etc., which the storage capacity of Frontier can't even handle because it doesn't even have that much storage capacity. Putting this goal back to the front burner of how we wanted to learn more about the dynamics of plasma instabilities, which means dealing with tons of data set. So where do we start and how do we do this? So coming back to the drawing board, we wanted to apply some machine learning to the problem. And this paper is accepted to IPDPS, which is happening in Italy early next month. And it's also a best paper nomination, so we're looking forward to giving the talk there. And this is about extracting knowledge from large-scale simulation using learning, machine learning. So here the goal is, there is two well-known shear surface which are usually observed in fluid and plasma. This visualization credit goes to Richard. This is running on 4 V100 GPUs. So when two layers exhibit different velocity and density, you see two shear surfaces, right? So this is the Kelvin-Helmholtz instability. It's being visualized, as you can tell. The KHI, it's driven by self-amplifying cycle of small density or velocity fluctuations, which can lead to a growing magnetic field at the shear surface, which further amplifies the initial fluctuations. So this is another beautiful visualization, which took us several back and forth, iteratively improved enough to demonstrate those two shear surfaces. So to deal with lots of data, to deal with in situ analysis across several nodes, the couple of frameworks we had used is OpenPMD, which is a data standard for particle mesh data, and ADOS2 in collaboration with Oak Ridge National Lab, which is an I/O library which handles data transfer, especially when you have volumes of data internode, right, between different nodes, lots of nodes. Also, the SST is the backend of ADOS2, which supports different types of implementations, multiple transport methods with Fabric MPI, etc. So Pick on GPU uses OpenPMD, formatted particle data from memory to one memory to another memory, in-process memory, using ADOS2 with an underlying implementation, be it libfabric or MPI. So the goal to do this, or the reason to do this, is to bypass the file system under the hood, which not only has only so much storage capacity, but it can also be slow sometimes, right? So some of the challenges we had with system constraints when we're dealing with this influx of volumes of particle data, which is about 5.86 gigabyte of particle data per node, per time step. This can lead to, creating terabytes of data set, but application scaling to just 25% of the entire system would produce about 1 petabyte of data every time step. But the Orion file system of Frontier at the max could write 10 terabytes per second, right? So 1 petabyte per time step, about 1,000 time steps, we're looking at exabyte of total data. So between 100 to 1,000 seconds, the total data volume would reach about 10 exabyte, which is in the entire file system, for example. So the entire file system can be actually exhausted in 100 to 1,000 seconds, right? So the question was, how do we circumvent this file system? How do we come about bypassing the file system without worrying about not enough storage? So this led to a couple of ideas. There is a paper on this. It's on arXiv. I think IPDPS hasn't put the published version DOI yet, maybe after the conference. So feel free to take a look for more in-depth details on this. But the bottom line is, between simulation and streaming and the learning, there are different ways to address this problem. You could do the streaming and the learning within a node among the 4 GPUs, or you could do streaming and learning among nodes, so inter-node, or you could do streaming and learning within the mixed format, right? Some in intra, some with mixed. So how do we schedule these jobs so that there is continuity in the simulation process, in the learning process, and everything still works without fail, right? So the only thing that we have explored so far among the 3 techniques is the first box that you see, where between streaming and learning, we bypassed the file system completely, the Orion file system completely, and in situ analysis, data is flowing data is flowing between among all the nodes, and the other pieces to explore yet that we haven't done is data reduction, and also the intra, or the mixed system of how do we schedule these jobs across full frontier, yet use Avios 2 OpenPMD to use these different nodes more efficiently, right? But there is more experiments to be done, and that's a to-do. So here are some experiments of data streaming on about 9,126 frontier nodes. It basically shows usage of libfabric as well as MPI. Bottom line is, we know that the particle data produced by PIC1 GPU is about 5.86 gigabyte per compute node in step. libfabric achieved about 3.5 to 4.7 in lower number of nodes, but only 1.9 to 2.6 when it's scaled up. Right, libfabric, as you know, we can do a lot more low-level, implementations, low-level optimizations. So TBD as to how we could bring this more at par. We are talking to HPE as we speak on what did we miss or how they can help. MPI did as it was supposed to do, so we have, of course, defaulted to MPI, where you see at 4,096 nodes, we see about 2.6 to 3.7, and it scaled better as you go higher up, right? So we were able to stream more data as we went higher up with MPI as the backend for the SSD engine. So that was a streaming. Now there is in-transit continual learning. There is a learning component for the streamed, incoming data. So here is where the model is continuously being trained online, subsequent snapshots of evolution of plasma, and at no point any data is being stored on the disk. So that brings us to the model architecture. There is a lot more going on besides what you see in this particular figure. Of course, you can see an invertible neural net, right? There is a decoder, there's an encoder, there is a 3D point cloud. There is a variable autoencoder as well, because we didn't want the INN to memorize incoming data set, rather be able to deal with a new incoming data set and be able to accordingly reproduce the input. Right? Yes, so there's a lot more going on. You see multiple layers there. You see a convolution layer, you see a deconvolution layer. There's multiple level of perceptrons there. And this alone took probably 6 to 8 months work. And still, we feel like there is a lot more that we could do. But again, the goal was not to exactly reproduce the input particles and the output particles, but use a VAE so that the model can learn and not memorize. The good part was our model fits into one GCD. As I mentioned, GCD, I have 2 in one GPU. So each copy of the model could receive different chunks of data, etc. In the interest of time, I will go a little faster. We did have issues with ML scaling, as you can imagine. So the in-transit learning trained from 8 to about 96 nodes, so it's not full frontier. But the streaming is what we demonstrated across full frontier, all the 9,126 nodes. The ML model scaled up until 100 nodes. And we are dealing with some, PyTorch libraries, kernel operation libraries that works well with CUDA, but they had issues with, when you throw them on an AMD GPU. So there were software compatibility issues between NVIDIA AMD GPUs, as you can imagine, right? Because not every library is looking for both the platforms. There were also inevitable all-to-all communication between PyTorch ranks, which during backward pass, there was a deficit of 30% of efficiency there. There were also, some performance issues with respect to some loss functions to compare point cloud. So all these, there are some outstanding issues that we are working with as we speak. And there's a lot more permutation combinations of experiments one can do to further, streamline some of these results. The takeaway from all this was, despite all the hiccups we ran into, INN model, inversible neural net model, was clearly able to partition the latent space into regions for flow directions as well as vortex regions. And both the parts of the ML system, the encoder as well as the inversion by an INN, figured out how to handle those zones correctly, right? So that's a plus. We couldn't achieve complete reconstruction because that's where we started, but we could do partial reconstruction, and the ML still predicted, or clearly identified the instability regions. So with in-transit in-situ analysis, with in-transit learning, we felt this was a promising early result using machine learning for one simulation. Especially, it's an ill-posed problem, as you can tell, and there's a lot of changing situations as we go. So this was, for us, a game changer to even realize that this is actually doable, right? And we could do further than this. So that's the overall workflow. As you can tell, there is simulation, there is OpenPMD, there is ADOS, there is particle streaming, there is PyTorch, there is machine learning, eventually to lead to some compelling results. All this code is open source. Every library used for Python GPU is on GitHub. Again, it doesn't stop there, right? So how could we, we did a partial reconstruction. How do we do a complete reconstruction? How do we build surrogate models of different configurations? Because these experiments can be quite expensive, right? So that's where the beauty of surrogate models come in. Then there are many more time steps that we could collect if we have, figured out how to do this even better. We still need to work on intelligently reducing data without losing useful info. There is valuable information that we learned from one simulation, but imagine there could be so many more simulations, there's so many more information that could be learned. We do need better decoders, we do need better encoders, and so on and so forth, right? So there's potential improvements every step of the way. Yeah. So that's my last slide. Thank you very much for being here, and hope this was fun.
All right. Thanks a lot, Sunita, for this great talk. Now, let's start the discussion. Are there any questions or comments? Okay, so I guess I'll start. So what would you say? I'll start easy. What would you say about the state of the tools in the AMD universe as compared to 6 years ago? Are they on par with the NVIDIA tools, or is there something missing, something you would wish for?
Excellent question. I would say that the AMD tools have come a long way from where they were 6 years ago. When we started, clearly everything was, in its baby versions, everything were failing, and there were more and more bugs than solutions. But I feel like the ROCm team, the HIP, the AMD software team in general, I think they've come a long way in the last several years. They've built tools that were non-existent in 2019, 2020 timeframe. Now there is RockProf, there is OmniPerf. OmniPerf still uses RockProf under the hood. And you can visualize a lot more performance details in these tools, and this wasn't possible even 4 years from earlier, right? So between CAR codes and ECP codes, we have probably all the application developers have provided a ton of feedback, and that has in the past years helped them improve their software stack tremendously. I shouldn't comment on if it is at par with NVIDIA tools, but let's say there's room for improvement.
Is there any intense connection or communication with AMD, with tools developers at AMD? Or is it just that you report bugs or feature requests and then it comes back from some kind of cloud? Or is there some direct connection?
Because this was part of ECP, right? And there is a ton of funding involved in ECP. There were regular back and forth with AMD developers beyond just bug fixing. There were several of us, I think I even gave a user talk in a closed door AMD forum, where the talk was not as pretty as you saw right now. It was complaints. It was a ton of feedback, right? And people like us encourage them to speak more and more and more with users in a more regular cadence. And I think they have started to do so in the last several years. Plus, there is Livermore's El Capitan as well, which is also an AMD system, right? So I think between them, between the LLVM open source community, where we push a lot of implementations, credit goes to Johannes Dofert, who leads the GPU offloading for OpenMP. We do the testing angle for OpenMP offloading implementations and a few compiler runtime implementations. Between all these efforts, I think we try our best to communicate to them about how there is room to improve the quality of software. We also share spec HPG results, for example, which has a dashboard of OpenMP offloading compilers of HP, Cray, NVIDIA, Intel, AMD. So you see comparisons, right? And I think it's important for them to know how their competitors are performing. So between ECP app developers and us, we have had a lot of one-on-one discussions with the AMD developer teams.
Coming to the performance of the code, you said at one point it's strongly memory bound. So did you actually observe, when you observed the performance of the code over the years, the per node performance, did you observe the proportional increase of code performance with the memory bandwidth, or do you actually not hit the roof line?
Well, we did compare, I didn't show that particular slide, but we did a smaller version of Picon GPU to compare the one-on-one with the V100 and MI250X, one MI250X. And I think it hasn't grown. I wouldn't say it has grown over a period of time. There are some memory-bound pieces within the code that we could probably revisit, how the data is flowing across the different memory hierarchies. So that's an algorithmic improvement we could consider. But I wouldn't say that it has grown in a period of time, but we can see there is a gap, right? For a long time, we couldn't put a pin on where the gap is because we didn't have the tools to poke into the AMD GPUs. So we invented our own Python script-driven tools and PyPlots to visualize what was happening. But if you put apples to apples, to V100, one V100 and then 250X, because that was our baseline, and the final form run, although it makes no sense to compare a V100 and 250X, we could see the proportionate increase in how the data is flowing between the different memory hierarchies. But I would say it is more consistent.
So if I understood correctly, then the network, the neural network fits on one GPU, okay?
On one GCD.
Yeah, exactly. Even that. So the learning, the data flow for the learning, that happens on the device. But the scaling bottleneck is actually the global communication that you need to put it all together. So that is where you investigated this libfabric versus MPI that we saw on slide 30. I'm a little bit surprised that MPI scaled better than libfabric. Why? What's that? Because for me, libfabric is something lower level.
Yeah, I don't remember on top of my head the bugs that we ran into with libfabric. Is anybody, the few on the call, but I don't see France. Is anybody on the call, HCDR folks, able to answer this question? Hey, Michael.
Hey. I think we had some issues with the libfabric installation first in PyTorch, as far as I remember. Yeah, that was one critical one I know, and there are also colleagues here that I see from our Plasma Pepsi Euro HPC Center of Excellence that have had a closer look at the comparison between MPI and libfabric, and in fact saw what you just alluded to, that libfabric would actually scale better. But I think there was more of a premature technical implementation of libfabric in this overall thing. We switched in between to libfabric, but one has to say, and maybe this would also be for the understanding, the code performance of the simulation, as well as the performance of the training, are parameters in a much more complex optimization space here, because you have data flows that are collective. Training takes quite some time and needs the data from the simulation, which is actually very fast, though it's memory bound, so could produce much more data than the ML system can ingest. So in the end, these are some of the parameters of the overall optimization. And to me, the real challenge is not whether libfabric performs a bit better in the collective operation, but the next to leading order is now, how do you distribute this wisely on such a system for such a specific workflow in order to optimize data throughput and in order to optimize time to solution? And this is quite substantial optimization problem in my understanding, because you can put the code everywhere, you can put the network everywhere, and you can choose where something is, and now you can choose all these different combinations and in the end see which is the fastest. And this is a difficult thing we have to tackle now. Yeah? And it just doesn't only depend on a few percent differences between two libraries. It is a very complex optimization problem in the end.
That leads to a different question also. How much of the overall simulation is ingested in one, like in the training of one part of the neural net? So that the part that runs on the individual chip, because you cannot afford to feed all the data from the whole simulation, which runs on thousands of nodes, into one GPU node just for the learning, for the conditioning of this one small network. So how much of the data is actually used per network?
Yeah. That's a very good question. I would say roughly, please correct me, I have to look at the team as well, but I think it's at least a compression factor of about 100, I think, if not more. Because one of the challenges, and was alluded to what Sunita has said, first of all, even if you put it directly on the same node, of course, you have the memory hierarchy already playing in. But then the training time is factors and orders of magnitude longer compared to what the simulation spews out. Mm-hmm. And we have a substantial number. So what we initially do is we have a large number of particles in the simulation. And particles are not a very good data structure per se. So 100 million, we are talking millions of particles for ML. Usually the best you do with ML right now with particles comes from LiDAR and fast recognition in cars of large particle collections in reconstructing LiDAR data and so on. But these are usually thousands or 10,000s of points, not millions of points. So the initial part that is of real importance is this encoder that really does a lot of compression on the data. But I think Sunita can say more on the workflow and the stream there. But we reduced significantly. That's the first step.
Yeah, I mean, it's about 5-point-some gigabyte particle per node, right? So that's what one node has. And within a node, how it is distributed, more fine-grained, I think we have to put a pin on. But that's something that would be good info to share.